Good morning, students. This is Addagatla Nagaraju, working as lecturer in electrical and electronics engineering, Government Polytechnic, Station Ganpur. So today we are going to learn DEEE fifth semester's AC motors subject. In AC motor subject, single phase induction motors chapter we are dealing. So in single phase induction motors, cross field theory and types of single phase induction motors we will cover. So in the previous class, we studied about double field revolving theory. Okay. What does this theory tells about? Into how many components he resultant stator flux can be resolved to how many components the resultant stator flux can be resolved. Two components. Are these two fluxes rotating or not? Yes, sir, rotating. So net torque on the rotor is zero. Why? The torque due to two fluxes are equal and opposite. How to produce torque on rotor? By giving an initial start to motor. So on completion of this topic, you will be able to know about cross field theory, cross-field theory of single-phase induction motors, types of single-phase induction motors. So, how to rotate the rotor? The stator coil wound for four poles shown here. This is the one coil, and this is another coil. This is another coil. This is another coil. North to south. Here, south north, north south, south north. North south, south north, north south. Alternating poles are north and south pole. North south, north south. Here alternating. So how to rotate the rotor? When single phase supply is given to single phase stator winding, stator coil carries current during first half cycle of AC through stator coil. Current direction is inward in the lower half of the conductors and outwards in the upper half of the conductors. Due to this current, flux is developed. The direction of the flux given by thumb rule. So, when single phase supply is given to single phase stator winding, stator coils carry current during first half cycle of AC through stator coil. Current direction is inward in the lower half and the conductors outward in the upper half of the conductors. So due to this current, flux is developed. The direction of flux is given by thumb rule. Fields due to stator conductor currents and the resultant stator field shown here. So here is the stator and the rotor. These are the resultant rotor forces. Both are in opposite direction. So both are in opposite direction, equal and opposite force here. Three are inwards, three are upwards. Due to inwards one directional force, due to upwards one directional force, both are equal and opposite forces. The direction of flux is horizontal, thus the north and south poles are established. Thus the net flux due to stator coil current is horizontal. Rotor flux, rotor receives power from the stator by transformer action. Direction of current in the rotor conductor is inward in the upper half and upward in the lower half. These currents also establish poles on the rotor flux direction given by thumb rule. It is also horizontal force. So rotor receives from power from stator by transformer action. Direction of current in the rotor conductor is inward in the upper half and upwards in the lower half. These currents also establish poles on rotor flux direction given by thumb rule. It is also horizontal force. Here. The fields of stator and rotor currents are aligned. Rotor conductors in the upper half are pulled downwards and in the lower half are pulled upwards. Here is the upper half pulled downwards, lower half pulled upwards. So net force on the rotor is 0. Give an initial start to rotor. The rotor conductors cuts the stator flux. EMF is generated in the rotor due to generator action. The direction of EMF is given by Fleming right hand rule. Current direction is outward to one side of the vertical axis and inward to the other side of the vertical axis. So give an initial start to the rotor. Rotor conductor cuts the stator flux. EMF is generated in the rotor due to generator action. The direction of EMF is given by Fleming right-hand rule. Current direction is outward to one side of the vertical axis and inward to the other side of the vertical axis. Okay, if we give some initial start, then these three are not under these three. So due to this, The rotor has low resistance and high reactance, so rotor currents lags the stator current by 90 degrees. The field of rotor current is at right angle to the field of stator current. Thus, the field of rotor is called cross field. Rotor has low resistance and high reactance, so the rotor current lags the current stator current by 90 degrees. The field of rotor current is at right angle to the field of stator current. Thus, the field of rotor is called cross field. Due to the cross field, rotor rotates. This is the stator current and flux. This is generated rotor EMF. The rotor current lags this generated EMF by 90 degrees. So, when rotor is given an initial start by some external means, then cross field is developed due to generator action. Cross field is present only when the rotor is rotating. Its field strength depends on the speed of the rotor. Induction motor must run at speed less than synchronous speed, so cross field is somewhat weaker than the stator field. So when rotor is given an initial start by some external means, then cross field is developed due to generator action. Cross field is present only when the rotor is rotating. Its field strength depends on the speed of the rotor. Induction motor must run at speed less than synchronous speed. So, cross field is somewhat weaker than the stator field. Thus, the rotating field produced is not constant magnitude but irregular. Thus, the torque is pulsating. The pulsating torque produces noise and vibrations, so they are set on a rubber or spring mounts to reduce the noise which is inherent. Thus, the rotating field produced is not of constant magnitude. As three-phase induction motor, it is a constant magnitude, but the rotating field produced is not constant magnitude. In single-phase induction motor, it is irregular. Thus, the torque is pulsating torque. This pulsating torque produces noise and vibrations, so they are set on rubber or springs mounts to reduce noise which is inherent. At standstill, no cross field is present, only pulsating field is present. So at standstill, no cross field is present, only pulsating field is present. So no rotation in the rotor. If the rotor is rotated by some external means, it will continue to develop torque in the direction of rotation. The torque is pulsating torque. This torque is pulsating torque. Requirement for producing rotating magnetic field. For producing a rotating magnetic field, two things are essential. There must be two windings. There must be two windings. They must have space displacement and also phase displacement of 90 degrees. So, for producing a rotating magnetic field, two things are essential. There must be two things. They must have space displacement and also phase displacement of 90 degrees. So, two magnetic fields. So, rotating magnetic field is producing, here rotating magnetic field is producing coming to the classification of single phase induction motors according to the methods of starting the resistance split phase motor or split phase motor capacitor start motor capacitor motor capacitor start capacitor run motor shaded pole type motor. So according to the method of starting resistance split phase motor or split phase motor capacitor start motor capacitor start capacitor run motor shaded pole motor. These five types of single phase motors available. Coming to the split phase motor, stator carries two things, two windings. One is main winding, another one is auxiliary winding or starting winding. These two windings are displaced in space by 90 degrees. So stator carries two windings. One is main winding, another one is the auxiliary winding for starting purpose. So it is also called starting winding. These two windings are displaced in space by 90 degrees. The rotor is mostly squirrel cage type rotor. This is the split phase motor or resistance start. This is the running winding. This is the starting winding. This is the split phase motor but capacitor start. Here is the capacitor placed in the starting winding. This is the centrifugal switch to turn off the starting winding in running conditions. So this is the running condition. So both are split phase motors. First one is the resistance starting method. Second one is the capacitor starting method. The rotor is the squirrel cage type rotor. The rotor construction is like a cage. These are the end rings. These are the copper bars. So it forms like a cage mounted on a shaft. This is the shaft. So laminations of armature core squirrel cage bars are embedded in the armature in these laminations. This is the squirrel cage type rotor. Squirrel cage type rotor. This is the resistance start split phase motor. This is the split phase motor having four terminals. So starting winding, running winding terminals. Resistance split phase motor phasor diagram. This is the applied voltage and applied current. So starting current, this is the running current and this is the total current. Total current and the power factor angle is around 30 degrees. Resistance split phase motor phasor diagram. For getting phase displacement, starting winding is designed as high resistance. Starting winding has high resistance. Okay, this is the main winding is reactance, reactive winding. Main winding current is high running current lags the voltage by nearly 90 degrees. This is the running current lags the voltage by nearly 90 degrees. Starting winding current is I starting. A running one working current is I running. So I start is almost in phase with Vt. I run and I start running current and starting current produces two fluxes. Two fluxes. They should have a phase difference of nearly 90 degrees per ideal split phase motor, but the angle between 20 to 30 degrees. So running and starting currents produces two fluxes. They should have a phase displacement nearly 90 degrees for ideal split phase motor, but in practical the angle is in between 20 to 30 degrees. The conditions of space and phase displacements are achieved, so rotating magnetic field is produced. Rotating magnetic field is produced. Motor develops torque. Split phase motor rotating magnetic field. So resultant magnetic field shown in the blue and black. I start and I run. Working principle of split phase motor. The auxiliary winding is not designed for continuous operation. Single phase supply given to the motor. When the motor picks up speed, auxiliary winding is automatically disconnected by the centrifugal switch. So the auxiliary winding is not designed for continuous operation. Single phase supply given to the motor. When the motor picks up speed, auxiliary winding is automatically disconnected by the centrifugal switch to prevent the motor drawing excessive currents to protect the motor winding from overheating. So, when the motor picks up speed, Auxiliary winding is automatically disconnected by the centrifugal switch to prevent the motor drawing excessive currents to prevent the motor winding overheating from overheating. Reversal of rotation. It can be obtained by reversing either main winding or auxiliary winding. Any one, either reversing the main winding or auxiliary winding, but not both. Coming to the advantages of operation: nearly constant speed, reversible at low speed, rapid acceleration, low cost. Operate at nearly constant speed, reversible at low speed, rapid acceleration, low cost. Repeated start or stop cycles heat the winding, high start resistance, less useful for large inner inertial loads. Split phase applications. Split motor are used in fans, blowers, washing machines, oil burners, electric tools. Electric tools, etc. Coming to the summary, we have discussed about cross field theory. We have discussed about types of single phase induction motor. Okay, types of single phase motors. So coming to the quiz, coming to the quiz, when the motor is at stand, receives power, still it form the stator by option A transformer action, option B generator action, option C both, option D none of this. When the motor is at stand, receives power, still it from the stator by transformer action or generator action or both non-transformer action. By the transformer action, EMF is induced. Okay. If it is generator action, then it will be a rotation. But motor is at standstill. So motor not rotating. So it is not a generator action. It is a transformer action. When the motor is at standstill, option A, cross field is present. Option B, cross field is absent. Option D, none of this. So when the motor is at standstill, there is no cross field. When the motor is in the running, in motion, then the cross field is present. So at standstill, there is no cross field. Cross field is absent. Cross field is absent. How to develop cross field? How to develop cross field? By giving an initial start to rotor, by giving an initial start to stator, none of this. So, by giving an initial start, by giving an initial start to the rotor, so rotor is the rotating one. So, initial start to stator is a stationary one. So, there is no initial start. Initial start to rotor only. When the motor is under running conditions, when the motor is under running conditions, rotor receives power from rotor receives power from stator by option A transformer action, option B generator action, option C both, option D none of these. When the motor is under running conditions, so rotor receives power from the stator by generator action. By generator, because rotor is in running condition, then the EMF is induced by generator action. When the motor is at standstill, then only transformer action is there. Motor is in running condition, then there is a generator action. So at standstill, transformer action, at rotation, generator action. When the motor is running, the direction of the rotor current is given by flaming left hand rule, option B flaming right hand rule, option C thumb rule, option D none of these. When the motor is running, the direction of rotating current is given by flaming left hand rule. For motor operations, flaming left-hand rule. For generator operations, flaming right-hand rule. For same also for DC machines. For motor, flaming left-hand rule. For generator, flaming right-hand rule. The angle between rotor EMF and rotor current So the angle between rotor EMF and rotor current. So for ideal rotor should be complete reactive winding should be 90 degrees, but there is no ideal present. Okay. For ideal, the angle between rotor EMF and rotor current is 90 degrees, but practical there is no ideal. It has some resistance, then it is nearly 90 degrees. Okay, because the rotor is a completely inductive nature, complete it has a reactance. Single phase induction motors are made self-starting by increasing rotor resistance, by using external device, by using auxiliary winding, any of the above. Single phase induction motors are made self-starting by using auxiliary winding or starting winding. Using auxiliary winding or starting winding. The two windings, main winding and auxiliary windings, are connected in parallel. Option A parallel, option B series, option C either series or either in parallel through inductive coupling. Two windings, main winding and auxiliary windings, are connected in parallel. In parallel. Okay. Connected in parallel. The stator winding of a single phase induction motor is splitted into two parts. Option A, improve efficiency. Option B, improve power factor. Option C, develop starting torque. Option D, increase speed. The stator winding of a single phase induction motor is splitted into two parts. Option A, improve efficiency. Option B, improve power factor. Option C, develop starting torque. Option D, increase speed. So to develop the starting torque, we need to split the stator winding. That's why split phase. One is starting winding, one is running winding. When single phase induction motor picks up speed, which winding is cut out of the circuit? Option A, rotor winding. Option B, main winding. Option C, auxiliary winding. Option D, all of the above. When the motor, when the single phase induction motor pick up speed, which winding is cut out of the circuit? So when the motor, when running condition, there is no need of starting. There is no need of starting or auxiliary winding. To improve the efficiency, to reduce the losses, auxiliary winding is starting winding is cut off by using centrifugal switch. By using centrifugal switch. In a split phase motor, in a split phase motor, the ratio of number of turns on auxiliary winding to the ratio of auxiliary winding to that on main winding is option A unity, option B less than unity, option C more than unity. Okay. In a split phase induction motor, the ratio of number of turns on auxiliary winding to that on main winding is. So auxiliary winding has less number of turns than main winding. Only for starting auxiliary winding we are using. So auxiliary winding is less than main winding, then the ratio should be less than 1. The torque speed characteristics of two-phase induction motor is largely affected by the torque speed characteristics of two-phase induction motor is largely affected by option A voltage, option B speed, option C X by R ratio, option D supply frequency. So torque speed characteristics of two-phase induction motor is largely affected by option A voltage, option B speed, option C X by R ratio, option D supply frequency. There should be a high reactance. So X by R ratio. X by R ratio. Split phase motors are seldom used in size larger than option A 1 by 8 kilowatts, option B 1 by 4 kilowatt, option C 1 by 2 kilowatts, option D 1 kilowatt. Split phase motors are used in size larger than 0.25 kilowatts, that is 1 by 4 kilowatt. Single phase induction motors are classified on the basis of option A construction, option B starting methods, option C size, option D RPM. By starting methods, option D both construction and starting methods. So single phase induction motors are on the basis of construction and starting methods. So we have discussed the starting method, but by construction shaded holes are there. By construction and starting methods they are classified. A rotating magnetic field is produced by current in the two windings displaced by 90 degrees. This is the principle of option A phase sequence, option B phase splitting, option C phase timing, option D none of this. So a rotating magnetic field is produced by current in the two windings displaced by 90 degrees is the principle of phase phase splitting. Split phase motors are there. When a single-phase induction motor picks up speed, its starting winding is disconnected and the motor continues run on dash winding. Option A rotor, option B armature, option C main, option D compensating winding. So it has two winding, auxiliary winding and main winding. So auxiliary winding is cut off, then only main winding is present, it running. In case of split phase motor, the split phase between current in the two windings is around option A 30, option B 70, option C 90, option D 120. It is 30. Ideally, it needs to be 90. Ideally, needs to be 90, but practically it is 30. Coming to the fill in the blanks, the main winding of split phase induction motor has high. dash dash resistance and reactance. So it has high reactance. Main winding has high reactance. The auxiliary winding of split phase induction motor has auxiliary winding in a nature. Resistive nature. Auxiliary winding has resistance. For ideal split phase induction motors, the angle between main winding and auxiliary winding should be 90 degrees. Ideally should be 90 degrees. The stator of a split-phase induction motor carries only one winding. False. It carries two windings. Single-phase motor has no starting torque of its own. Yes, it is true. Split-phase induction motor, the auxiliary winding has lower resistance to react as false. Split-phase in a split-phase motor is done by transformers. False. In case of one-phase induction motor, inductance may be used in series with the main winding. Inductance, no. Auxiliary winding is true. Cast field is present when the rotor is running. Cast field is absent when the motor is standstill. The strength of the cast fields depends upon the speed. Cast field is somewhat less than the stator field, weaker. Dash is the reason for noise and vibration in the single-phase induction motor to pulsations. Reversal of direction of one-phase induction motor should be done when the motor is at rest. These are the frequently asked questions. Okay, thank you.